Greetings, everyone. Time to begin our 1:30 press conference, which is going to be about improving forecasts of storms called Pineapple Expresses. And I've been hearing that the rain in California this past weekend and into Monday is an example of this kind of storm. And I guess it's related also, there's storms in England recently and Wales that were also this kind of storm. So our speakers are going to be in this order. Marty Ralph, he's a research meteorologist and chief of the Water Cycle Branch in the Physical Sciences Division of NOAA Earth System Research Laboratory in Boulder, Colorado. Speaking second will be Kevin Baker, meteorologist in charge of the San Francisco Bay Area National Weather Service Forecast Office in Monterey. Then Mike Anderson, of the he's a California State climatologist with the California Department of Water Resources in Sacramento. And our last speaker will be Michael Dettinger. He's a research hydrologist with the U.S. Geological Survey and a research associate with the Scripps Institution of Oceanography in La Jolla, California. Our speakers will all speak, and then we'll open the floor to questions after that.
Greetings, and thank you for coming. We're here today to announce the development of a state-of-the-art observing network that's being installed in California to monitor conditions we now refer to as atmospheric rivers. An example of that is up here on the screen, where you can see the amount of water vapor over the ocean, primarily, is shown here over the Pacific with the blue colors. I'll get the trackpad going here. The blue colors are dry. The green is pretty moist, yellow is very moist, orange is moist, and red is extremely moist. And what you see here is a loop over about the last 2 weeks showing the structure of those water vapor fields over the ocean. We've come to learn now different patterns in that data that allow us to interpret the presence of what we call atmospheric river conditions. Now, an atmospheric river is a region in the lower part of the atmosphere, in the lowest roughly 5 to 10,000 feet, where most of the water vapor is transported in this part of the world. When that feature lines up and hits the coast, it can produce large amounts of rain, which frankly is what we just saw the last few days here in California, and that's what this loop represents. And I'd like to highlight this region right here, hitting the coast just a moment ago. That's the one that just hit on Sunday. Here's the first one that hit up in the Pacific Northwest, right around Thanksgiving, as you may recall. And then the next one moved north over the eastern Pacific, but didn't really hit the coast until it swept through Thursday night. The next one lined up here and hit, and then the third one lined up here and hit. We see this now in these kind of observations and in these numerical models, and it's really helped us understand the causes of extreme precipitation and in many cases flooding in the West. It turns out that atmospheric rivers are the cause of most of the floods in the western coastal states, much like we've seen just in the last few days. Now, the network, that imagery illustrated what we see over the oceans primarily, and there's observations out there from satellite that help us, but those observations don't work over land. And here's what we're doing in terms of fixing that problem. What's highlighted here is a network of over 100 stations that are being installed right now. We're about 3/4 done, and what we have are measurements of atmospheric river conditions at the coast. Those are the yellow circles. The first one of those is being installed later this month on the coast just north of here at Bodega Bay. This whole network is based on lessons learned from our NOAA project called the Hydro-Meteorological Testbed with our partners at Scripps Institution of Oceanography, at the National Weather Service, and at the Department of Water Resources in California. The blue squares here represent what are called snow level radars, and these measure conditions aloft that help us tell us how high up in the mountains is the conditions producing rain versus snow, and that's critical when it comes to floods. The atmospheric river observatories tell us what's going on in the winds aloft, well above the surface, right in the altitude range, about 5,000 feet up, 3,000 to 5,000 feet up, which is the core of the atmospheric river. Other points on this figure represent soil moisture measurements. It turns out the last month or so, we had a series of storms that moistened the soil here. We could see that quantitatively for the first time, and we knew that coming into the last few days' events, the watersheds were primed for some pretty severe runoff if the atmospheric river conditions did occur as were predicted. And then the other dots are another measurement system that allows us to see water vapor from the surface to space. That's called integrated water vapor. And that's a measure of how much juice is available for one of these storms to produce precipitation. The highlight here, as I mentioned, is the Bodega Bay site that's going in later this month and will be installed under support from the Department of Water Resources in California and with NOAA and Scripps, as I mentioned. What does one of those snow level radars look like? Well, it looks like a bit of a cheap kind of thing, and that's exactly what it is. It's a culvert pipe from highway construction, wrapped over with boat wrap, but inside that are two little radars, one looking up, that transmits the signal, and one that receives it coming back. What that does is allow us to see in the bottom left here, these black dots represent the altitude of snow transitioning from snow to rain. This is altitude on the left, and what we see is the snow level changes with time. It can drop thousands of feet in a matter of a few hours or climb thousands of feet, and these make a big impact on the flood potential. And you can see the design here was represented an award received for the good work. In addition, these atmospheric river observatories are consisting of wind profiling radar, and that's what's shown in the bottom right here. This grid here transmits a signal upward into the atmosphere. It reflects off the turbulence in the air or off the precipitation in the air and tells us a lot about the winds aloft. And we can monitor those winds every hour without a person standing there. It's an automated system. And you can see here the schedule for our installation is starting this month and going through about a year and a half from now. I won't go in detail on this, don't worry, but what it shows you is the output of years of development on the observations in the top part here of winds aloft, time going from right to left, and we have thresholds here of water vapor and wind information and then precipitation down here. The punchline being is we've developed a forecast decision support tool that weather forecasters and others interested in the upcoming events or the existing events can use to help make decisions about their operations, whether it's a flood control decision or an emergency evacuation decision or agriculture, any sort of folks who need this type of information. If we look at the event that just happened, here are some of the new data that we have. Once again, about 3/4 of this network is in place now. And what you see on the right, don't worry about the details, is the raw data. And those black dots tell us the snow level. And at the most recent time of those observations, this was from yesterday, I've shown in those black arrows the pointing to the location where the measurement was made and the altitude of the snow level at that time. And this just really goes to illustrate the range of conditions that occur in a typical event. With just about 4,000 foot snow levels up north, that means altitudes in the terrain higher than 4,000 feet are receiving snow. And you look down south here towards Lake Tahoe, we're looking at close to 9,000 feet. What that means is most of the watersheds, most of the area in the watersheds in that part of the Sierra were exposed to rain rather than snow, and hence there was a lot of runoff. In addition, what does this look like over the ocean? Here's a satellite image showing the atmospheric river conditions. But what does that look like over land? Notice it's black in this. That's because the satellite method doesn't work over land. It's just a technical issue. So we've filled that in now with a network of over 50 sites that are going in not only in California but across the West. And these now show us what's happening at the coast and inland in a level of detail we hadn't known before. And the red colors here represent the large water vapor contents associated with the atmospheric river hitting central and northern California. Notice the blue colors up here, that's the drier conditions further north and a bit drier in Southern California as well. So this very recent case illustrates some of the new information that we're able to provide at this point. And I'd like to go ahead and turn it over now to Kevin Baker, meteorologist in charge of the National Weather Service Forecast Office in San Francisco, Monterey.
Thank you, Marty. Yeah, this, as many of you who've been around here the last few days have noticed, if you've been in the Bay Area, the rain we've had has been quite intense, and these are largely a response to the atmospheric river events. Back on, well, it would have been right after Thanksgiving, the Saturday before Thanksgiving, we started to notice in the forecast models and looking at some of the tools Marty's provided, we noticed the potential for an atmospheric river event developing by the 28th of November, which was last Wednesday. So the forecasters began advertising this event about 5 days before it happened, and this was the first, as it appeared to be, in a series of atmospheric river events, which, as we saw, went all the way through yesterday. We started putting out messages on social media using Facebook, Twitter tweets, YouTube videos. In fact, my warning coordination meteorologist here, he actually produced a really nice YouTube video in layman's terms, which you can get to from our Facebook sites and learn more about these events. We also issued statements, watches, warnings. We mentioned atmospheric rivers in our forecast discussions as well, and emphasized the potential for heavy rain, strong winds, and flooding. Here's one example. This is one of the atmospheric river Facebook posts we did, and you'll see in there there's some details about the events and the types of weather impacts you can get from these atmospheric river events. We also had a number of likes. We had over 40 likes for this particular graphic and a number of comments. In fact, we found out this morning that site or that post has received over 1,000 views so far. So a lot of people are showing interest in these atmospheric river events. Kind of a summary of what happened over the last few days. The first event was very fast moving. On Wednesday, we had about 1 to 2 inches of rain in the North Bay. The winds were a big issue that day. We had quite a few gusts over 60 miles an hour, uprooted trees, power lines. Some folks were without power after that event. That one moved through very quickly, so we didn't get the really large rainfall amounts from that. It was much more of a wind event. On Friday, we had a much heavier rain event. We started getting some flash flooding reports. As you see in the graphic there, we had over 7 inches of rain in Santa Cruz and the Santa Lucia Mountains. That event actually ended up moving a little bit further south, and Monterey County mountains had quite a bit of rainfall from that. And also the North Bay got hit. Over 6 inches of rain was observed up in the northwest corner of Sonoma County at Venado. And then, as many of you are aware, yesterday we had another very similar event with a lot of rainfall, very intense rainfall. Fortunately, the system moved through fairly quickly and what could have been a lot worse rainfall. But by Sunday, the ground was already very much saturated, and we started to seeing a lot more down trees from the wind gusts, which were also quite strong. And my understanding is in the Bay Area we had over 35,000 people without power at some time yesterday. So, in summary, 5-day event rainfall amounts were in excess of 15 inches at Mount Umunum, Venado, and Mining Ridge, which is down in Monterey County. Very impressive rainfall amounts, comparable to some of the big convective storms or thunderstorm type events we see in the East Coast. A lot of street urban flooding. Even some mudslides were reported and road closures and downed trees. And the atmospheric river research that Marty and his group have done has been excellent. It's really helping us to the forecasts have a better idea, kind of a conceptual model of these type of systems coming in and the potential for heavy rain and a lot of weather impacts. So that I'll turn it over to Mike.
All right, thanks. So, excuse me, I'm with the Department of Water Resources, and we've had the good opportunity to be involved reviewing the research done by Marty and participating in the work they've been doing over the past decade here in California. And then we had the opportunity to take advantage of investing in the elements of this that proved to be ready for operations. And we see this network as having application in many parts of the work that we're doing within the Division of Flood Management and other parts of the department, and some of them are listed here. The Flood Response and Preparedness program, where we're looking to find ways to improve the forecasting abilities, improve our warning time, be more accurate as to where we expect specific impacts to occur. We see this helping in flood planning as we move to try and develop a more physical basis for our flood mechanisms, in part to not only look at what happens now, but to plan for how to designed for a flood of the future with climate change involved. And the figure here kind of shows some of our expectations of climate change effects on water resources. And this network gives us an avenue into measuring some of the physics that would go into that to be able to monitor change. This will also help our coordinated operations activities within the reservoirs of the Central Valley, which will help manage water in the managed system in the leveed part. Again, this also provides information for water supply forecasting, giving us a better feel for what the watershed condition is prior to the snowpack setting in, and facilitating getting the timing and volume aspects down during the spring melt. And as I mentioned earlier, monitoring climate change so that we can start to track more than just precip and temperature, but to really understand this aspect, as I said, can relate back to some of our flood planning activities, particularly as we move forward with aspects like the 200-year urban level of protection. And with that, I'll turn over to Mike Dettinger.
So just to take it back to the network, Marty did a great job of showing us the various pieces and telling us somewhat how they interlock, that sort of thing. I just wanted to summarize with just largely this simple graphic that is to give you the logic, to kind of remind you of the logic of this network that we're putting into place. As it says here, you know, a simple-minded recipe for a flood in California is you need the soils to be wet enough so that the precipitation that falls doesn't just get soaked up into the soils. You need the precipitation to fall over large areas as rain rather than snow, and then you need a lot of water to fall out of the sky. The new network, well, you get all those pieces together, and you get a flood in California, and some of our floods are really very large. The new network kind of follows that logic. We have, as Marty said, something over 100 stations collecting different kinds of data now that are going in as part of this network. Soil moisture monitoring across the whole state. The statewide snow line information. This will be at 10 different major reservoirs around the state to allow us to have a better sense of how much of their catchments receive rain rather than snow in real time. And then also the water vapor coverage over the state to fill in what we can't see once the water vapor gets off the ocean. There are several things that happen here. One is the statewide coverage. These are coming, this network is growing out of what Marty referenced as the Hydro-Meteorological test bed, which is focused largely in the American and Feather rivers up in northern and central California. We're taking this statewide at this point with this network. It's also just the fact that we're taking things that were learned in this HMT research and making them operational is a major step forward. One thing to understand is that these technologies, even these technologies here, really weren't in our hands. They weren't possible just 15 years ago for the most part. They were either too expensive or else the technology simply didn't exist. And so we're moving with things that we've learned from Marty and the crew in the hydrometeorological test bed, and we're making those operational and statewide. And then finally, the thing that brought us here today was the beginning of the installation of this picket fence, I like to call it, of some 4 or 5, depending on how you want to count the locations, atmospheric river observatories strung down the coast so that we can look into the heart of these storms in real time and better understand what's going on in them. Now, a lot of this is here to support better forecasts from the Weather Service and the river forecast centers and the like. But I contend that each of these things, well, these data are going to be available and are available now in real time to the public. And I believe that water agencies all over the state are going to rapidly develop their own rules of thumb for their own backyard as to how wet the soil has to be before they have to be worried where the snow line has to be for a particular storm for them to be worried, and so on. So this is a major step from what was a research effort that began 10, 15 years ago to an operational network for the state that we frankly can be very proud of.
We're ready to start with questions from the press, and please remember to identify yourself and your media affiliation.
Rick Lovett, freelance. I was in Sacramento yesterday at the marathon with a bunch of people who mostly came from the West Coast, and something was different about this weather forecast from anything that most of us knew. And I'm wondering whether you got lucky or something new was online. I mean, I was up on this, of course, because everyone was obsessively looking for what the weather was going to be at 7 a.m. And to our dismay, you nailed it from way farther out than we would have believed. So what's different?
I'll mention, really one of the things that was different with this event is it was very well forecast. I don't know if you can, there we go. It was very well forecast by all of the longer range forecast models, and the integration of data into it, such as this, into the models is essential, and it really does help improve the forecast. And the models have gotten a lot better with time. And as forecasters, one of the things we're looking for is consistency from model to model and run to run. They run frequently, at least once every 12 hours, we'll get a model run. And there was a lot of consistency in this case, and that really builds our confidence. And quite often, the forecasts work out very well when that's the case. The challenges are when the models are forecasting a lot different solutions, and it's much more challenging. Some of these bigger events, too, are usually well forecast by the models.
Yeah, I'm Dave Perlman from the San Francisco Chronicle. First of all, that great vibrant graphic of that greeted us as we came in, is that online so that we could,
yes.
we could push our readers to, hey, take a look at this? Okay. How strongly will, or how much will the new instrumentation improve forecasting, improve determining whether a storm is accompanied by high levels or snow or low levels of snow, all of those details that go to make up the flood that was also on the graphic?
I think one of the things that's critical is out over the Pacific Ocean, we have very little data to begin with. And we're pretty much relying on satellites. And the integration of this kind of information is critical to improving the forecast model for just the forecast in general. So any additional data we can get is a huge resource to us in helping us improve our forecasts.
Oh, excuse me, go ahead.
I could add a couple of anecdotes from experience. One was in the case of the snow level, a storm was approaching the coast, and the expected snow level, this was a couple years ago when we were demonstrating the technology and the science, was predicted to be about 6,000 feet. It ended up coming into the coast at more like 3,000 feet. What that meant was it went from a winter storm watch to a winter storm warning, and that the passes, and this was in Oregon, the passes were going to end up being inundated with snow rather than with rain. So there was a lot of implications of that, that particular event in snow level.
Would you explain how low was the snow level? Is this in Oregon?
This was in Oregon in that case where it came in at 3,000 feet above sea level rather than 6,000, which was originally expected. And that made a big difference. You can imagine passes at 4,000 feet or 5,000 feet. In one case, you don't need snowplows. In the other case, you need a lot. Another event happened up in Washington State, and this was a very important illustration of the kind of decisions that can be made. There was a dam that protects Seattle from flooding, and it's done so for 50 years. But it was damaged during a big storm in 2009 to the point of being declared unsafe. So for the following winter or two, many people, and since that dam was put in place, the watershed was built up. The floodplain was built up. Microsoft, Boeing, cities, and the like. Turns out that we were able to deploy some of these equipment up to help out in monitoring ARs as they hit the coast. The forecast offices up there did a lot of other things as well. Luckily, they didn't get hit really hard. The dam's been fixed. But in the process, the Army Corps of Engineers started looking at these observations from the Atmospheric River Observatory and realized in one case where they were about to take control of a dam for flood control instead of water supply, that the atmospheric river back edge had just passed a couple hundred kilometers west. So they decided that the storm was going to let up soon enough that they didn't need to take over flood control operations. This is a big deal in the water business, and it turned out to be the right decision. So there are a couple of concrete examples of specific decisions that have been affected by these kind of data, although they haven't been, those were cases elsewhere at this point.
I'd like to pile on a little bit there, because Marty made a transition there that I want to make sure is clear. When you think about forecasts, there are at least two aspects that are important to us. One is getting the weather right, and it's often difficult to be sure how this data really impacts the models because it goes into them in a fairly tortuous way. But the other aspect of forecast is how much flooding and how much flow and flooding are going to result from it, what the impacts will be. And this network is really tuned in many ways towards setting us up to do that in a very direct way to improve our ability to forecast what a particular storm will mean in terms of floods.
I'm Horst Rademacher, Frankfurter Allgemeine Zeitung in Germany. I have two general questions about atmospheric rivers. You speak of rivers, so if you look at the moisture content that gets transported, can you compare that to the Amazon, to the Congo? I mean, how much water is in these rivers? That's the first question. And the second question is, are there any other parts in the world where you have these rivers, or is it only here in the East Pacific?
I'll answer the second one first. There are researchers now in Europe and South America who are publishing papers in the peer-reviewed literature finding atmospheric river conditions as creating extreme events, both in the UK and in Chile and South America. It's quite clear that the phenomena occurs across the globe in many locations. Once you get up into the polar regions or down right into the heart of the tropics, they're not so important. But in the mid-latitudes, where many of us live, they're a vital part of the water cycle. In fact, 90% of the water vapor transported in the mid-latitudes happens in these atmospheric rivers. And these atmospheric rivers are fairly narrow, and they represent less than 10% of the circumference of the Earth if you add up their width around the planet. So these are really the engines of the water cycle in the mid-latitudes. How much water vapor do they transport? Massive amounts. It turns out if you look at an average AR, as we call them now, that hit in the Eastern Pacific, it'll be transporting the equivalent of 10 times the average water flowing from the Mississippi River into the North Gulf of Mexico. So 10 Mississippis is a shorthand for that. That's a heck of a lot of water. It turns out another way to express that, and this is a term water managers are familiar with, is about 10 million acre-feet of water in a day. The entire runoff of the Colorado River Basin for an average year is 15 million acre-feet. So effectively 1 or 1.5 typical ARs transports in the atmosphere about as much as the entire Colorado River does in a year. In the Sacramento River north of here, or I'm sorry, we're not in Sacramento, the east of here, it's about 20 to 25 million acre-feet per year of runoff. So not every drop of water vapor in an atmospheric river rains out, of course. And it turns out the preliminary studies are looking at about 20% or so. So if you do the numbers, and we have maybe 6 to 10 ARs will hit Northern California in a given winter, that adds up to something like 10 to 15 million acre-feet of rain. And that's about half the runoff of the Sacramento River. When we look at rain gauge data around the state over 60 years or over many years, we see that about 25 to 50% of the entire water supply for the West Coast states comes typically in about 6 to 10 AR events over the course of the winter at a given location. So they transport huge amounts of water vapor. They affect not only the West Coast of the U.S., but the West Coast of other continents as well.
May I ask one clarification? You said 20% of the water vapor falls as rain on the average in an AR event when it hits land?
A preliminary study that has been published did conclude that, yes.
Harvey Leifert, Freelance. I have two quick questions, or at least I think the answers will be quick. The first is there any correlation between Pineapple Expresses and El Nino or La Nina years in terms of their frequency or severity? And the second is, I'm not quite clear on the statewide snow line detectors. Are they detecting precipitation or what's on the ground?
The snow line detectors or snow level detectors are detecting above the ground. If you look up in a rainstorm, if you were able to go up, you'd see that the temperature gets colder as you go higher. And eventually, when you get high enough, it turns to snow. And that's what we call the snow level. So it's what happens is the snow forms high up, and as it falls, eventually it warms up and starts to melt. And when it melts, the droplets form and they accelerate. There's a very clear signature in the observations of that feature.
So it's what's falling.
It's what's
It's the
falling.
distinction between snow falling and rain falling, rather than what's on the ground.
And the El Nino?
Can I do that one? Yeah, so what we've seen, there have been studies, Marty led one in particular, where we've found that during El Nino sorts of conditions, sometimes some of the most intense of the atmospheric rivers occur. That's because the water vapor in the tropics is sort of sitting in the right place to get swept up into one of these things. On the other hand, on the long haul, over the last 60 years, what we find is that in Southern California, there's a statistical relation between La Niñas and increased contributions from atmospheric rivers to the total precipitation. But up here in northern and central California and most of the way up into the Pacific Northwest, there's no clear connection over the long haul, over the 60-year sort of time scales.
Rick Lovett again. This is for Marty. You mentioned and I've got another question too, but you mentioned a river in Washington. What river was it, and what's the dam?
The Green River, and it's called the Howard Hansen Dam.
Hi, Kit Stoltz, Ventura County Star. I wonder if you could talk about costs, or I guess I should say spending, for this new network, first of all.
All right. So we've been engaged in a 5-year project for installation of this network, and the investment of the 100 or so sites amounts to about $11 million.
Okay, very good. And well, naturally, with global warming, we should see more water vapor in the atmosphere, and one wonders if there is an increased contribution to atmospheric rivers.
So we've looked in a half a dozen, actually in 7 of the climate models projections for the 21st century climate. And what we've found is that as the atmosphere warms, it does indeed hold more water vapor, and therefore the atmospheric rivers get juicier. The catch is that at the same time, the winds that are blowing these kind of weather systems tend to slacken a bit, to weaken a bit. And so that would tend to carry less of that juicier air into the coast and that sort of thing. What we found over the 7 models that we've looked at so far is that taken together, wetter air but moving slower, the wetter air wins out, and these become a little bit more common and a little bit more intense. They carry more water when they show up. And in both cases, when I say a little bit more, I mean something on the order of maybe 10% more on average from model to model to model.
If I could just add a couple things real quick. One is we failed to point out that there's a web page that NOAA's produced for atmospheric rivers. If you Google NOAA Atmospheric Rivers information page, you'll find a lot of information and references to papers that Mike has produced and others, for example. I also want to make mention that Mike Dettinger and a colleague are co-authors of a paper, is it okay for me to mention, that's coming out in the next issue of Scientific American on the role, I believe, of atmospheric rivers in large floods.
Yeah. December 20th, I think it hits the stands.
Dave Levitan, freelance. I'm just a little confused how the the new network of sensors and array of instrumentation actually helps predict or forecast storms? Is it by adding historical data to a model, or can you just explain that a little bit?
Yeah, actually, the information that's received, any data source like this will get integrated into the forecast models. It's a starting point for the models to go out and forecast, hopefully more accurately in the future. And this kind of information is going to be critical to improving those forecasts, because you need data to start with to get a good forecast.
If I could add to that, Kevin. There was just run what was called an atmospheric river retrospective experiment, forecasting experiment at the Hydro-Meteorological Prediction Center in Washington, D.C. And what this did was take advantage of the atmospheric river observatory observations we've had in place for quite some time as part of the forecast process. One of the things specifically it helped with was to quantify the onset time of AR conditions at each of the locations and the end time. And it turns out, and research, I'll be presenting an invited talk this afternoon, that the duration of an AR at a given location is critically important in determining how extreme the precipitation and flooding will be. So these AROs are vital for determining that.
Rick Lovett again. Yeah, that was related to the question I was going to ask, but I'm going to ask mine, which is a little more detail-oriented anyway. I am confused about like the snow line predictions. It seems like I presume these are short, these radars are looking straight up, so they're telling what's happening above it. So I'm confused on how that gives you a forecast of what's going to happen in 2 days, because it seems like you'd want to know where it is out over the sea.
Can I run with this?
So you're the mic.
So what these do is these provide initial conditions for the model, and establishing clear initial conditions, particularly as you transition into the Sierra, enables the modeling then to move forward from there to get that freezing level more clearly. The model that the Weather Service run carry out the forecast, but these data points help initialize that, and a better initial condition will lead to a better forecast.
And I'll just add, reiterate a point I made earlier, and that is that, that's weather forecasting. The forecasting of the impacts, the runoff, the flooding, that sort of thing is directly, it may not buy you 2 days, but it's directly related to things like how much of the basin is getting rain rather than snow. And so this can improve our ability to know what's going on right now and what kind of flows that will ultimately mean.
Another aspect of that is that in the short term, say the 6 to 12 hour time frame for a streamflow forecast, it turns out the end of an event, timing that and understanding when it's going to occur is vital for major high impact decisions on reservoir operations. I remember hearing from a fellow who was involved in the 1997 flood that nearly inundated Sacramento about a few years before Katrina. And it turned out that they had been considering opening the floodgates to a larger level than they normally would, because that level would create flooding downstream. And they faced a very difficult decision. Would the storm end soon enough to allow them to not have to make that very destructive decision? Basically, would they sacrifice homes and the public downstream to save the dam? That's the kind of decision that's made. It's not very often, but when it's made, it's incredibly impactful. So the snow level is a key bit of information over the few hour period to 12 hour period where those types of decisions are important.
Do we have further questions from members of the press?
Yeah, hi, John Karachuski, freelance. In a sense, you answered the question, but do you have other examples of rain on snow? And it sounds like you were addressing that in the 1997 one with Folsom Dam.
Mike, do you want to mention this?
I'm the worst person to ask this, because I think that rain on snow is really overhyped, quite frankly. I think that in the case of 97, it wasn't so much that there was all the snow was melting, it's that the rain was falling over the entire basin instead of maybe the lower third of it, and as would be more normal in a normal storm. And it's actually kind of difficult to come up with really clear examples where the rain on snow has increased the flows by more than, say, 10 or maybe 15%. They typically don't overwhelm the rain contribution.
Yeah.
Although there were a couple of examples in December of 1955 and 64 that were huge storm events, especially in Northern California. And I'm not knowledgeable, but my impression was that those were attributed to rain on snow.
Again, when I look at the data, I don't necessarily see a clear-cut case for that. I know that at the time they were attributed that way, and I'm really reticent to say from a lifetime away that I somehow know more than they do. I will say, however, that both of those were atmospheric rivers, if that helps.
Just adding to Mike's comment a bit, and Mike has impressed upon me the numbers associated with the snowmelt. Fundamentally, if you put very cold rain on snow, it doesn't have a lot of energy available for melting. But there's another process that people are starting to look at, and that is the condensation of vapor directly from the air onto the snow itself. That releases a lot more heat than the sensible heat of the rain itself. And there is some research going on in that area. I don't know that the numbers are out yet in terms of the contribution, but think of it as warm, moist air flowing over a snowy ground can potentially lead to more melt than even if you had rain going at the same time.
Okay, we have time for one more question.
My name is Danielle Venton. I'm with KRCB Radio. I was wondering if you could just run by us some of the specifics about the network again, like the types of stations, how much is left to complete, how they're connected.
I can do it if you want. Go ahead. Yeah, we're putting in 4 atmospheric river observatories on the coast. Their spacing is about 250 kilometers apart, which is about half the width of an average AR. We're also putting in 10 snow level radars running from the very northernmost part of the state to the southernmost. And then we're putting in 36 of the GPS MET receiver sites. And also there are a number more that have been added since then by other organizations. And then also 43 soil moisture sites around the state. One
clarification, GPS MET measures the total water vapor in the atmosphere. That's what
Thanks,
that
Mike.
measurement is.
Okay, and I think we had one more question back here. Yeah, I think we do have time. That was pretty short.
Hi, it's Hunter Cutting. I'm a blogger with Climate Nexus, and I was trying my hardest to go through your paper about how climate change might impact atmospheric rivers in the future. And I understand, as you described, there's this, marginal but significant difference on the overall average, but I do understand that there's some rather perhaps large changes in the frequency of the most extreme events. And I was wondering if you could talk about that and also talk about how maybe your model, this observing network, how it was designed to track the most extreme events that we may be seeing more of.
So, as I said, we've done an analysis of 7 models to look to see what happened to atmospheric rivers under climate change. And on average, the changes are relatively small, as in 10 or so % increases. At the same time, if you move beyond just looking at the average conditions, the average over a bunch of atmospheric rivers, and look at the entire distribution, one of the things that was noted was that in nearly all of the models, I believe it was 6 of the 7 models, that if you looked out at the largest atmospheric rivers that were being simulated in the historical period, versus at the end of the 21st century in these various models. What you found in 6 of the 7 cases, 6 of the 7 models, was that in the future, at the end of the 21st century, you would see one or two, just a very few, 1 or 2 cases of atmospheric rivers that were carrying anywhere from 50% to 100% more water than the largest ones seen in the historical simulations by these same models, even though the historical simulations that we were comparing to were actually about twice as long as the part of at the end of the century, of this century that we were looking at. So it had twice as many opportunities to pop off a really large atmospheric river. But in 6 of the 7 models, what we found were the really large ones showed up at the end of the century, of this century, which seemed to suggest that although there weren't enough of them to change the average by much, the global warming is likely, I'm hesitant to say likely, in that the analysis continues with more models right as we speak, but is likely to add in a few megastorms, if you will, of a scale that we may not have encountered historically.
Okay, that wraps up how much time we have for questions from the floor. So thank you, panelists, for your talks and your answer. We're going to have a next press conference will be at 2:30. It's about winter is coming, but what happens when it leaves early. So please come.